Right then, so today we're looking at perpendicular bisectors, and one of the most important goals for us today is to find the equation of a perpendicular line segment. We want a standardized routine for that one. But when it comes to our analytical thinking today, this is where it can get really tricky with this one. We need to solve problems involving shortest distance from a point to a line, and constructing and analyzing perpendicular line segments. So we really have to sort of be on our game to understand the concepts here on this one today to make sure we can apply it in problem-solving situations. So we started off first with a bit of an investigation, trying to come up with a problem that we can solve and see if we can find our way through it. So we have two towns, C and D, and they're to be serviced by a new railroad. Town C has the coordinates 2, 10, we can see it here in the diagram, and town D has the coordinates 10, 14, and the railroad roughly follows the equation of a straight line, y equals 2x plus 3. So a train station is to be built on the line, which has to be equally distant from both towns. So we have to figure out how we're going to do that. How do we place a point on this line somewhere so that it is equal from both sides? So I have no idea how to do it. So I'm going to start thinking my way through the problem. And a good place to start maybe is to use a ruler and say, well, what happens if I go from this point to this point in a straight line? Obviously, this is the shortest distance from C to D, but it's not going to be equally distant from both of these 2 points, is it? It's not going to be equally distant from both points. So how are we going to do it? How are we going to find the line? We're going to do a perpendicular bisector of this line. So imagine that line drawn there. What we're going to try and do is we're going to try and draw a line which cuts that line exactly in the middle. So firstly, we're going to need to do a couple of things. We're going to need to find the middle of this line, which is around about here. This is the middle of this line. We're now halfway between these 2 points. But unfortunately, that's not on the railroad. So we need other points which are halfway between these two, but on this line. So what we do is we take this point, which is the midpoint, and we find a line that goes through this now, like this, which is a right angles to that. We find a right angled line here. So then we find, where does this line cross? Because we are equally distant from D to M and C to M. Now, any line along this is going to be, we go to here and here. These two lines from C to A and from D to A are also the same length. You can see it a bit happening here in this diagram. You can sort of visualize it. So if we can find this line, we can find that particular point. So let's have a go at this. So firstly, what did I have to find first? I have to find the midpoint between C and D. Well, that should be straightforward first. Have a go now at finding the midpoint from C to D. Take a minute. I won't pause the video on this one. Take a minute now to find the midpoint of C and D.
So can you give me the passcode?
I'll have to do it after the video. Okay, so we should find the midpoint fairly easily for this one. We add the 2x coordinates together and divide by 2. We add the y coordinates together, divide by 2, we get the coordinates of the midpoint, which is at 6, 12, and when I spotted it. I actually had the midpoint in exactly the right place. Lucky. So now we need to find the equation of this line, which goes through M and A. We need to find the equation of this perpendicular line that goes through M and A. So in order to do that, we only have one point on the line, and we need to be able to get access to the gradient somehow. We can't, but we can find the gradient of the line CD. So we are going to find the gradient, M, or we just do a lowercase m. We're going to find the gradient of line CD first. We're going to find the gradient of line CD. Have a go at that now. You have the information necessary. Find the gradient of the line CD. Take 1 minute for this one. It's easy. Okay, so we need to find the gradient of line CD. That means we need to find the change in y values and the change in x values. So the y values have gone up by 4, and the x values have gone up by 8. So the equation here is going to be a half. This gives us the equation of the line CD, and we want the equation of the line that's perpendicular to that. So we need to find the negative reciprocal to get the perpendicular gradient. So this implies that the gradient of the perpendicular is going to be the negative reciprocal. It's going to be -2. Now we have the gradient of this line. We can find the equation of the line because we have the gradient and we have a point. The midpoint is a point on the line that we're after. We're after the line MA. So we can find this as a perpendicular. We'll use point slope form. So we're going to go through 12, y equals 12. It's going to have a gradient of -2, and it's going to go through x equals 6. This is the equation of the perpendicular bisector. And the whole point in this is we are trying to find where this point intersects the line L. And we're given the line L. The line L is given in the question. So we need to find where that line that we've just made intersects with this line here. So we want to form these two. Sorry, we want to form these into an equation system. Form these into an equation system, and we can solve this on our graphing calculator. So take out your graphing calculators now and solve this equation system. Just going to pause a second for this one because I want to come around and check everybody solves the equation system. Okay. So we need to solve this equation system on our calculators. So we start by pulling up our calculator like this one. As I've said before, I always recommend not using the scratch pad, but using a proper document. When you're starting a new piece of work, press on. Press 1 for new document, say no to saving the previous, and always start by adding a calculator. I say that every time. So now what we need to do is solve an equation system. We press menu, algebra, system of linear equations. This one's going to have 2 equations in the variables x and y, so we're all good to go. And then we type in the equations as we see them. Y minus 12 is equal to -2 times bracket x minus 6 close bracket. With this calculator, I usually recommend when you have a number outside a bracket, is to always put in the multiplication that is implied normally, because sometimes it will get stuck on some things. I think when it's graphing, it will sometimes get stuck on that one. So always put the multiplications in. That can be often why it's refusing to do what you're expecting it to do. Then we put in the second equation, we press enter, we have our two answers. So if I want this as a decimal, I press Control Enter, and I can see the two values now written as decimals. I'm just going to put those in. So this is 5.25, comma 13.5. And those are actually exact values, I can tell by fractions. This is the coordinates of a train station is to be built on the line L, and it's equally distant from both times. This is the coordinates of the train station. Yes. As mentioned before, you can always give answers as an exact answer or round it to three significant figures. A fraction is an exact answer. This one is actually an exact answer, although you might not know that, but I can tell by the fact that one of them is a quarter, 0.25 is a quarter, and one of them is a half something, 0.5 is a half. I can see that these fractions and those decimals have been rounded.
For me, I only got answers with this.
That's fine. It's to do with the settings that you have on your calculator. They will vary depending on what settings you have.
And it's fine if I just put the decimal.
You can always answer with a fraction, an exact answer, it's like a fraction or a radical. You can always answer rounded to three significant figures unless the question specifically specifies it's something else. Right, so that's that problem finished. Let's go through this in a little bit more detail now. So, this one is the basic routine. You've just seen me do finding the equation of a perpendicular bisector and using it in a problem-solving question. That's a little bit more challenging. That's the big picture that we're aiming at, the analytical problems. Now this is the raw routine. What were the steps I did? What were the steps I did to find the equation of this line? This 12, y minus 12. What did I do first? Find the midpoint. What did I do second?
You calculated C.
I found the gradient of the line CD. What did I do next? Find the equation of the slope of the bisector, the perpendicular. So I did this bit here, this bit here. So number one was this, number one, number two, number three. And then plop it in here, number four. Have a go now, see if you can remember that routine and apply it to this non-problem solving standardized question. Okay, so here's the necessary steps to this standardized algorithm. So we want to start by finding the equation of the midpoint of the line segment AB. So the midpoint is going to be 1 plus 5 over 2, negative 1 plus negative 3 over 2. That's going to give us 6 over 2, which is 3, minus 4 over 2, which is minus 2. So we have our midpoint. Next, find the gradient of the line segment AB. So now we need to change the x and y values. So the y values are negative 3 minus negative 1 over 5 minus 1. This is going to give us negative 2 over 4, which is minus a half. We want the perpendicular gradient. I like to show the little perpendicular symbol in the subscript. Explains what you're doing. And that one's going to give us 2. You take the negative reciprocal. Finally, make the equation of the perpendicular bisector using the point slope form. So y1, y minus y1. y1 is negative 2. 3. Reread the questions before you finish. It says find the equation of a perpendicular bisector. This is the equation of a line. We don't need any specific form. This one is good enough for us. Okay, so let's look at the concepts. One thing a lot of people get confused with at this particular point is how we mix and match the different words. So in this diagram I'm showing you, this is a bisector. So we have the line segment AB. Any line that goes through the midpoint is a bisector of line A and B. So let me just show you. If we have the line A and B, any point going through the midpoint here is going to bisect the line. So we can have a bisector. It cuts the line in half. We can have a perpendicular bisector. This one's going to cut the line in half, but there's only one answer here. So there are an infinite number of bisectors of the line segment AB, but only one perpendicular bisector. The perpendicular bisector goes through the midpoint at 90 degrees. And then the last example, this is a perpendicular. We sometimes use a perpendicular to solve the problem. We don't always use a perpendicular bisector to solve the problem. Sometimes we use a perpendicular to solve the problem, depending on the situation that we're looking at. So this is where it gets a little bit tricky. You have to decide which of these three lines to construct in order to solve your problem. And that you only really get from context and understanding, and that's where the analytical approach is required. So going back to today's goals, when we talk about the analytical thinking, you have to solve different types of problems. There isn't a standard answer. Sometimes you will need the perpendicular bisector, like this one, and sometimes you won't. Sometimes you'll need the perpendicular to solve the problem. Both a perpendicular and a perpendicular bisector cut the line at 90 degrees, but only one of them cuts it at the midpoint. The perpendicular bisector cuts it at the midpoint. Yes. Yes. So a bisector cuts a line segment at the midpoint. A perpendicular cuts the line segment at 90 degrees, but only a perpendicular bisector does both. What are the properties of a perpendicular bisector? So perpendicular lines, these are useful for finding the shortest distance from a point to a line. So, for instance, we will use this one, the perpendicular. We'll use this one, the perpendicular, when we want to, let's say we wanted to travel from this point here in the shortest distance to that line. We would only be using the perpendicular. This will get us the quickest to the line GH from this particular point. This would be a perpendicular. So the perpendicular will give the shortest distance from any point in the coordinate plane to a line. You want to listen to this bit carefully because it can get a little bit tricky. So let me explain what it's saying there a little bit. Let's do a little bit of a diagram. We have 2 points like this, and we wish to find the shortest distance to the line between these 2 points from some third point like this. So you would find the gradient of this line. You would find the perpendicular that goes through point C, like this one, AB, and then this distance here would be the shortest distance. Now that is easy to a line. To a line, this is always the case, to a perpendicular. But let's say you have the same problem, it's A and B. What if point C is here? What if point C is here?
Isn't that like what we did on the first question?
No. That one's quite a different problem. That's a problem of equidistance, not shortest distance. We're looking for the shortest distance from the line between A and B from point C. Now in this particular case, let's see if we can see it. The line AB is like that. The perpendicular is over here. That is not going to be the shortest distance to the line segment AB because it's not on the line segment AB. If you're talking about a line segment AB, the line segment AB ends here. So the perpendicular is not going to help you. The perpendicular it doesn't, then the shortest distance is the line AC. You have to go direct. So if you want to make it really tricky, then you have to consider these two possibilities. So this is all about, near the keywords, shortest distance. Perpendicular, shortest distance. Now the perpendicular bisector is a different problem. This one is all about equidistant, equal distances. So look for it won't necessarily say these two words in the question wording. It's possible to set up a problem where you then interpret, am I looking for an equal distance or am I looking for the shortest distance? And that will tell you which of the two methods to use. So what's special about the perpendicular bisector is that all of the points on a perpendicular bisector are equally distant from points A and B. So if we look in this diagram I've shown here, you can see the point A and B, and then we have the perpendicular line through M. Any point on the line M is equally distant from the points A and B, as you can see in these two examples shown here. I made a little bit of an animation of this one. So any points on this line are going to be equally distant from points A and B. Watch how as this moves along, they always have the same length either side. You can see that every point along this line is going to be equally distant. And let me just show you why. So if I put a point here like that one, it's going to go through here and the lines will stop to go through that one. Why is this the case? Well, it's all about circles. So if I draw a circle here through that one, notice it goes through A and G. If I draw one through B and G, these two circles are going to have the exact same radii. So this line here is the radius of the circle. This line here is the radius of the same circle. And these two circles have exactly the same, radius. That's how we construct it. All right. So in summary, perpendiculars are good for shortest distance problems, perpendicular bisectors, and good for equally distant problems. Have a go at your last problem for today. It's a problem-solving question. I'll note myself to record it today. All right. Work together in pairs, see if you can solve the problem. This takes 6 or 7 minutes for this one.